Okay.
Yeah, I didn't record it, so but it's okay. Yeah.
Okay.
So but that's for the game. Yeah, for another example, if
That's Bayesian.
yeah, this is a
Using
of course you can also yeah, if you want to go for map, then in that case you should find a mode instead. But I think like if you just check Wikipedia, also like it should show you what's the mode here, so we don't need to compute it. So mode is so I think it's alpha over beta is the mean here that we use alpha over beta. The mode is alpha minus 1 over beta. So or our a minus 1 over b then. Yeah.
so in the inference like this, the first thing we should find the prior that will be same to the
Yes, we want to find a conjugate prior.
Yeah.
Of course, you can just go for Wikipedia, but at least you want to understand what does that mean. So after that, like, you know what does that mean? Like most of the time, probably you can just go look it up. Like what was the conjugate prior? Of course, I also you need to see. I want to show this example because you see, like it depends on what kind of parameter you're estimating, right? If you're estimating a mean, even though you have the likelihood is a Gaussian distribution, whether you're estimating the mean or you're estimating the variance, the conjugate prior can be different. Yeah. In the first case, we are fixing the variance and estimate the mean, then the conjugate prior is simply another Gaussian.
Yeah.
But here, like if we fix the mean and want to estimate the variance, the conjugate prior will be the gamma distribution.
But the distribution is still same, but the result is different mean and.
No, you mean the pi distribution? The pi distribution is not the same, and of course the posterior won't be the same also, right? Here, like in the second case, your prior now is a gamma distribution, right?
Yes, that's right.
In the first case, the prior is actually another Gaussian, right? This is another Gaussian.
Yeah.
It's just another Gaussian.
Another question. So it means that the prior the likelihood should be similar with the prior. So we should choose the prior first, really similar with likelihood, and can we go that not conjugate likelihood?
Conjugate prior?
I mean, yeah. Can we choose another? I mean, that not conjugate, just any prior.
You can, but no one do it because that's no point to pick another pi is not conjugate to, because then what you get is something. Basically, you won't be solvable.
Yeah.
Here, it make it much more easier. Right? It's extremely simple.
But, okay.
Yeah.
I think how to describe it. So we like this. This is our prior. Our prior is A. Our likelihood is A, and it should be this is our prior. Our prior is similar to this one, but it is different value. Mu 1 and zeta 1, something like that. And if we put another mu 1 and sigma 1, that will be get another result.
Yes.
Also.
Yes.
But this is still same type.
It's still a conjugate pi, right?
Yeah,
You're
conjugate
still
pi.
same form, but that's exactly what we're doing, right?
Yeah.
Here, like we have this mu lot and sigma lot is like the
Yeah.
hyperparameter, right?
But the type of this one and this another one is still same, but different result.
Yes. You change this mu lot and sigma lot, this hyperparameter will affect the final result.
Okay.
So but yeah.
So there is another problem come up from there, something like what is the best one of hyperparameter?
No, I guess this is kind of difficult to say. I guess it probably will become domain knowledge. It will depend on your problem, I guess. So I don't know. Like I don't have a good answer for you. Like because for example, like you think of like tossing the coins, like you really cannot kind of justify which player will be like the best. Yeah.
That's right.
So it really depends. Like the prior itself is your prior belief, right? What do you believe? I mean that would be like really the domain knowledge. Like for example, like for you have some kind of model and you are working on this and you believe like this is more likely to happen, therefore you impose a prior like more bias into that outcome, stuff like that. So for example, like you if go back like the beta prior, I can put different A and B here, right?
Yeah.
And A and B is in the sense that I don't need to have the con to be fair to start with, right? If I put in a different A and B, then basically it won't be a unbiased con. It can be a biased con as well. So therefore, like whether you want to choose like the con to be biased or unbiased to begin with, like that depends on your belief, right? So therefore, like you cannot. I mean, that's no. I don't think that's a good rule of thumb. Like you need to look at like that's exactly the domain knowledge that you need to.
Or maybe just our beliefs come from the previous time series.
But then that is still domain knowledge, right? The previous experiments they accumulated like by previous scientists is essentially like the domain knowledge, right? They did the experiment in the past and then they have those beliefs and then you use their beliefs.
Yeah. Use this belief, use the previous belief to get another belief.
Yeah.
Another future.
Okay, so I have very few times left, but I guess I just use my remaining time to give one more concept that you may come up with like in the future. It's like exponential family. It's a exponential distribution. It's like honestly, almost all distribution will fall in this exponential family. Like with a few exceptions, for example, mixture of Gaussian. And if you look at almost all distribution like Gaussian, like beta or like gamma, all of this like it will be like falling into this exponential family. And actually, like what does that look like? It is basically have a form like this. Will be something like hx g theta exponential theta phi x. So we call it exponential family because I probably because of this exponent here. So phi is some like observation function. So this can be a vector here. So you can have multiple observation. So you have phi x can be a vector also. Like you can have 5 is basically equal to phi 1.
That is
Phi 2.
modified Gaussian.
No. This is a general distribution.
General distribution. So what
This
is
they have exponent here.
what is theta here? What is the p?
These are parameters. Theta is some parameter here.
So we have 3 parameters.
There's some parameters here.
One,
Phi here is like
1, 2. 1, 2.
phi is like some observation, some okay. X is yeah. Phi you can consider as some observation. Like you have x here, and you or some function compute on x, then you have phi, and this can be like vector. So therefore, like this phi in general can be like theta 1, I mean phi 1, phi 2, phi 1, phi 2, and so on.
So phi is observation.
Yeah. I guess I would just consider it as observation. So then and then theta is like some parameter here, and g theta like you can think of like g theta is some normalization factor. Like we'll explain more later on. Like I probably like cannot explain a lot. We only have 10 minutes. So and hx. So anyway, we have a shape like this. Okay, it looks kind of weird, like, but I guess like one nice thing is like we learn something that like give a motivation why we have something like this. Remember that like in homework exercise, when we talk about the conditioning limit theorem, right? So if we have computing, we have some random variable, let's say x, and let's say for this random variable we have some pi distribution hx for that one, and we say that if we have some observation, like or like we for this outcome, like we try to compute the phi 1, phi 2, and so on, and let's compute the expected value of those guys.
So why you want to get expectation?
Why you want to? Okay, let's just say that I do that, like whatever. So let's say I have an x, phi x.
So in here, what is this? Hx in here? This is just a function.
Hx is the pi. Hx is okay. Let me remind you like what we learned like several classes before. Like in the conditioning limit theorem, I think it's also occur in your midterm, right?
Yeah.
So basically, let's say if you have a variable that have a distribution of x, so then I have some kind of like compute phi 1 on x here, and then like if I kind of sample this many times, let's say you remember like if I sample this many times, and then like I compute the average of this x. Let's say I have many times, so xi I equal to 1 to n. I take the average of that. This should go to the expectation, right? Expected value, right?
Yeah, that's right.
So it should be typical.
Even any p
Yes.
in there.
Yes,
any p
but if I put in a constraint, let's say I put in constraint. Remember, I can put in constraint such that like this does not go to the average, but instead I go to some value is bigger than equal to ai, let's say a1. Remember that? Then in that case, I will have the distribution of this x will not be the original pi distribution, right? And then it will be have a distribution, have a form that hx kind of proportional to hx exponential lambda sum lambda phi 1x, right? Do you remember that? Right?
If we more than this,
Yes.
this one more than this, so this will be something like this.
Yeah, remember that?
Yeah.
Yeah, kind of remember that, right? That's exactly here. That's exactly here, right? So if we have n observation here, like so, we have how many? So let's say here I have a k observation here. So this will be like a k somewhere lambda 1 or theta 1 plus theta 2 find 2x, right? And so on, right? Vk. And this is just the inner product, right? Inner product of theta 1 up to theta k and phi 1
In the what?
inner product
Oh yeah, in the product.
phi k x, right?
Yes.
And then I have hx here is proportional to this, right? Hx is the original distribution, right? Now I normalize this, right? I normalize this, so therefore the final distribution should be like this, right?
Yeah. Should be like that.
Or like I will just write at theta.
So the check in here is original distribution.
Yes, you can think like that. Like if we interpret like this, you can think like this, right? And this guy here, the normalization factor, because I sum over x, right? It does not depend on x anymore, but it depends on theta. So it would be a function of theta, like it would be like some c theta, let's say, right? And this exactly equal to this g theta in the sense that g theta equal to 1 over z theta.
But this still there is x in there. There is an original.
Yeah, this is original. That's x here. Yeah.
So we can create any original distribution become like this.
You see, that's why this is so general.
Yeah.
Basically, like almost all distribution can be write in this form.
Yeah.
So let me give a quick example. Like I don't really have time. So just trying to do Gaussian. So Gaussian, right? Gaussian x mu sigma square 1 over 2 pi sigma square exponential minus mu minus x square 2 sigma square, right? Then I can write like 2 pi sigma square. This is 6. I just expand that. I have minus x square 2 sigma square minus mu square over 2 sigma square plus x mu sigma square. Then I can I have basically exponential minus mu square over 2 sigma square is a constant. I can put it out here. And I have exponential
X.
let me write so more on this. Yeah, x square, right? Basically, it's an inner product between
What you want to make
mu
in the product?
sigma square, or like let me write 1 over 2 sigma square first, and mu over sigma square,
That's right.
right? And x square and x,
Oh, yeah.
right?
Yeah, that's right.
Right?
Because that this and
Right.
this.
So therefore, this is the phi x, right?
Yeah.
There's a phi x. This is the theta.
Phi x.
Yeah, phi 1 and phi 2.
Oh.
Yeah, okay. And then this is the theta, and this is the whatever. In this case, I group together. So this whole thing here is the g theta. I mean, this case hx is just equal to 1. So 1. This is hx.
Oh, okay.
So this will be the
Yeah.
yes.
But how if there is not an exponential?
That is exponential. What do you
Like
mean?
that, for another something like uniform.
Oh,
Uniform.
uniform.
Yeah.
Okay, uniform.
distribution. How to
Uh,
create that then?
can I do that? I'm not sure actually. Uniform. Uniform may not be actually. You're right. I don't think uniform is like can be written in exponential form probably. But most distribution can.
So this is only for exponential family distribution.
Actually, not just like, for example, like let's give another simple example. Like I have binomial.
You will also using exponential.
Yeah, binomial you can write exponential, right?
Yeah.
Yes, and you know you. Then I'm not going to do it then. Like, binomial can do it also, right? So and beta, like you can do it also.
Yeah.
Gamma you can do it also.
Yeah. Something like there is no exponential in there.
Yes, many of them you can do it like this. Let's see. And of course wait a sec. I probably don't have enough time. I'll jump to of course if you have the exponential family form, you can like write down the conjugate pi right away. So let's say like I have
If there is no exponential.
we have like some, let's say some hyperparameter. This is some hyperparameter like I'm going to specify later on, but this is the posterior here. I will try to estimate those theta here. This is proportional to, let's say, I have like nth observation this time. So n observation, this is exponential family multiplied by theta. This is the prior, let's say with some hyperparameter, prior parameter is like alpha
So
and
you
nu
want to
here.
know
That,
prior.
yeah, we will want to write down this prior distribution. So then like this basically have a form like this, right? I have n observation here, theta, some exponential theta phi xi, right? And then and this I can multiply by
So what
p
is
theta
this?
of a nu, right?
So this one is this one?
Yes, this one is this one. This one is this one. So because I n observation, like they again use Markov property, like I can multiply them together. And this is a plotted h xi g theta to the n. This is exponential theta sum over phi xi, something like that. So anyway, I want this guy multiply this guy still have form like this. So what we can choose is we can choose a p theta.
Where it come from? Big sigma.
Oh, this is just getting inside, right? So
Oh yeah.
sum over like this sum over this is product, right? So therefore becomes sum.
Oh yeah, this one.
Yeah. So now this therefore we can pick like for example like this as a g theta to the alpha exponential theta alpha nu. So this will be the kind of the conjugate pi for that. So this you can interpret this as like the you have like alpha so many of additional observation at the beginning, and then the observation will be nu, something like that.
So you mean that you want to this one is similar to this one, and this is the conjugate prior to this
Yeah,
one.
in conjugate pi, like if you multiply by this guy here, then you still have a form like
Yeah.
it's like still this guy,
Yeah, and this one is this one. Yeah. That's
and basically the posterior then like will be has a form like now you have a original parameter is alpha and nu, right? After multiplying that, you have alpha plus n here. You have n additional n here, right? And also like the nu will become like
But that is this is the integration. This is the integration of this one. That's right. This is integration.
no, it's not integration. It's like just coming from this step here.
Ah.
This step coming down here.
Okay. Oh yeah, I see. And then
So, but now I have this guy. I decided this as my conjugate prior. Now I multiply by this guy.
there is n. This is n power. This one power n.
Yes.
Be more-
Yeah, but yes, you multiply this guy, you get like, okay, let me just multiply like that. When you multiply this together, then you have like g theta alpha plus n, right? So therefore the parameter become alpha plus n, right?
Yeah.
And then this have like still have product hxi, something like that. This is a exponential
Yeah.
theta. You have this alpha nu will add this guy, right?
Yes.
So then the new parameter will become like something like sum over phi, let's see, nu plus phi xi, probably over alpha, something like that.
Yeah.
I probably have some mistake here, but yeah, you get the idea.
Yeah.
So
That is you want to calculate the expectation, the mean.
after you, this will be the posterior, right? The new after taking the oscillation into account, then you have this new posterior, right? The posterior still have the same form, like a conjugate pi. And then with that you can compute the mean and variance, right?
Yeah.
Of course, here compute the mean and variance maybe of the conjugate pi directly may be complicated, but I mean of the exponential family may be complicated just in this form. But what I mean is basically everything in exponential family there will be a conjugate pi automatically. So I guess I'll just stop here, but yeah. At least
5 minutes.
Yeah. Yeah, I think it's already overtime. So, but I guess I'll just stop here. So, I guess that's the end. So remember, there's still like one assignment like this Friday, and
What is my
yeah, you already submit your
homework?
yeah homework, and also like final project due like next Friday.
You mean that you will send again homework?
No, I'm not going to send any more homework.
Oh.
Yeah, that's the end.
Okay.
Yes, okay.
Yeah.
So, okay.
Yeah, interesting the letter homework.
Yeah. Yes.
Okay.
I should like put more emphasis on the later part. I didn't expect
Yeah, maybe there is no explanation about how Pyro can do that.
prior. This one prior. There's
Pyro can do that.
a pyro. Yeah.
How? Yeah, I mean that.
Yeah. Don't have time for that. Yeah.
Okay, maybe.
So, yeah. Maybe in the future. Okay. So I'm just going to stop here now.